A very good morning to all the participants. You will get your registration ID from Google Classroom. We have already shared your registration ID on Google Classroom as well as on WhatsApp group. So you will get your ID from that group only. Shabir sir, shall we start now?
Yes, please start.
Good morning, Trapti ma'am. A very good morning to one and all. On behalf of Electrical Engineering Department SCET and our entire team of FDP, I warmly welcome our eminent speaker, Dr. Trapti Jain. She is an associate professor at Department of Electrical Engineering, IIT Indore. She is also Vice Chair, PES IS, Joint Chapter IEEE Bombay Section, India. She has completed her PhD from IIT Kanpur. She has more than 24 years teaching experience. She is member of board of directors of MBP KVV from 23rd May 2015. Her areas of interest are related to with power systems subjects like power sector, deregulations, artificial intelligence applications to power systems, power quality monitoring, microgrid, etc. She has published 4 books, book chapters at international level. She has published more than 60 papers at various journals and conferences at national and international level. Today, she will share experience on AC microgrids, islanded operation of microgrid and their optimum control. Madam, we are delighted to have you with us. Thank you. Over to you, ma'am.
Yeah. Thank you. So I'll now share my screen. You can just let me know if you are able to see it. So can you see the presentation?
Yes, ma'am. Visible.
Yeah. So welcome you all to this session, and I'm going to talk about AC microgrids. So based on this topic, let me show you what I'm going to cover in this talk. So we'll first see how the concept of microgrid came, okay, or briefly see the evolution of microgrids. Then what are the different types of controls in microgrids? Why are they important? And especially what is the main issue when the microgrid is operating in islanded mode? Though there are several issues, I'll talk briefly about them, but the stability is the most important issue when the microgrids operate in islanded mode. So that I will cover, and then briefly I will show you the controller design also. Okay, so there are several possible designs of controller possible, but we have designed in a different way, and that I'm going to show you in this talk. Okay. So let us see first about the microgrids. So why this microgrid concept came? Actually, first of all, we'll look because it is somehow related to renewable energy sources also. So why we started looking for alternative energy sources, isn't? So the motivation or the reasons to look for alternative energy sources were global warming and the continuously increasing demand for energy and depletion of fossil fuels, because we have limited reserves for fossil fuels, and we know that it will not be able to meet our continuously growing energy demand. So that was the reason we started looking for some alternative energy sources. Okay, and these are renewable energy sources which will not deplete, which will always be available with us. And these renewable energy sources, they are called distributed generations. Okay, why they are called, we'll see it little later. So what are the other forces behind the evolution of distributed generation? So distributed generation here, I mean not only renewable energy, but why? Because distributed generation, if some of you know about it, it is related to you are connecting them in the distribution network also. Okay, so we'll see these are all the reasons related to distributed generation, which includes renewable energy sources also. Okay, so what are the reasons? So first is like ever increasing demand for energy. So we all know that the technological innovations and the continuously rising temperature and continuous increasing use of electricity powered devices, all these are responsible for the increased energy demand. So all these are responsible because of these things, and rising temperatures. So people are also using ACs continuously, and then GDP growth. All these factors, they are responsible for the increase in energy demand. Okay, so that was one of the reason. Then we have constraints on construction of new transmission lines. So basically these constraints are related to environmental as well as economical. So environmental constraints include, like, it is difficult to get the clearance to construct the new transmission lines, and the main thing is right of way problem to get the land acquisition. So it is difficult to construct new transmission lines. Another one which is related to economics is it requires the construction of new transmission lines require large expenditure also. Okay, so it is a large investment which needs to be made to construct the new transmission lines. So because of this, people were thinking if it can be avoided. Okay, so then concerns over fossil fuel depletion. So obviously, as I told, that they are limited. So and the increase in demand is there. So to meet that demand, we were looking for alternative energy sources. Then inefficient transmission of bulk power over long distances. So if we see the centralized, it is always preferable actually that the generations and the load centers should be close to minimize the losses, transmission losses. But if you see the centralized generation structure, then the generation sources are far away from the load centers, isn't it? So that involves the losses also. So it is preferred that if the generation sources are nearby to the load center, then it will be good. Then increased awareness of greenhouse gas emission. So as we realized the harmful effects of greenhouse gas emission, the continuous steps have been taken worldwide to make more, to create more awareness about their harms. Okay, so different policies have been made, and which forced us to think about the alternative sources. Then liberalization of electricity industry. So you know already that worldwide the competition has been introduced in the electricity industry, expecting that it will lead to reduction in energy prices. And the other point is, so if the competition, it will be more effective if you have large number of players, then only it will be effective, otherwise not. So this distributed generation, these are basically small scale generations. So they take, means it is easy to construct them because their deployment time is, construction time is less, and they involve less amount of money also in construction as compared to the large power plants. So it was easy to incorporate them in the market structure. Then more focus towards energy efficiency. So this increasing the energy efficiency is considered as one of the most important step in reduction of CO2 emission. Then development, so in distributed generation technologies, so the recent advancements made in distributed generation technologies made them more attractive to use, to install in our distribution network. Then increased customer demand for highly reliable electricity. So these days customers are also highly willing to have high reliable electricity. Is it? So actually you must have noticed that even if a power goes out for a small time, the people, they are just like, why it has gone? It is not going usually, but why it has gone, even if it is going for a short time, even the kids. So everybody wants to have reliable electricity. So this all these factors motivate us or forced us to think about the distributed generation. Isn't? So here, like, we have considered distributed generation as either the renewable energy sources or they are connected in the distribution network. So we'll see like what exactly is the distributed generation. So there is no consensus on the definition of distributed generation. So different researchers have taken different definitions, and in fact different countries have considered different kind of distributed generations. Like some countries have considered on the basis of voltage level, Okay, some have considered if the generation source is connected in the distribution network, then it is considered as the distributed generation. Some has considered that if the renewable power generations are there, then it can be considered as the distributed generation. So there is no consensus on the definition of distributed generation, but IEEE defines distributed generation as generation of electricity by facilities that are sufficiently smaller than central generating plants, so as to allow interconnection at nearly any point in the power system. Okay, so these are small capacity generation plants. Okay, so that you can connect them at anywhere in the power system, and it will not be like, it is easy to interconnect them at nearly any point. Okay, so that is the distributed generation. Okay, so it is not necessarily, it includes renewable energy sources, but it is not necessary that it will be there. Even if it is like a diesel generation, which is of small capacity, you have connected it in distribution network, that will be distributed generation. So the power generation from DG unit, it is a small scale which ranges from broadly, it is no like consensus is there on this range also, but it varies from 4 kilowatt to 10 megawatt, then it can be considered. It will fall within this range. Okay. And these DG units, they are mainly classified into combined heat and power, where from a single source of energy, both electrical and thermal energy are produced, and renewable energy type, which requires power electronic converters for their interface. Okay, so these are the DG technologies which are usually considered. So this reciprocating engine is there, which is like almost 100 years ago, and among the first in the DG technologies. Then microturbines. So microturbine are the emerging class of DG technologies, which I think varies from 30 to 1000 kilowatt. And fuel cells. So fuel cell also, it was actually the first fuel cell was developed in about, I think, 1839 by Sir William Groves. Okay, but its first practical use was in 1960s when NASA used it for generating electricity in its spacecraft. Okay, so that was the first practical use of fuel cell. But nowadays, actually, there are a variety of fuel cells are under development. Okay, and then renewable energy sources. So they consider the solar, wind, micro hydro all can be considered as DG technologies, maybe geothermal and biomass, all they can be considered as the DG technologies, because the power generation will be in small scale range only. Okay. But like solar, if you consider a large scale, then it will not be DG. You must have heard about solar tower power also. So that will be large scale power generation, that will not fall under DG, distributed generation. So now what are the problems with the direct integration of DG units? So why can't we directly integrate them into our grid? So these DG units, they produce either a DC or a variable frequency AC. Okay, so we cannot directly integrate them to the grid, but they require a front end inverter to interface them with the distribution network or the local loads. So we cannot directly integrate them. Then other thing is this RES-based DG units, they produce fluctuating active power because they are intermittent in nature. So the active power is not constant, or we are not able to control. So it is fluctuating. Okay, so we cannot directly integrate them in the grid because we need to have control over this fluctuation also. Then because they inject the power into the distribution network, there are certain power flow problems also, which we have to find the solution. So it is not easy to integrate them directly into our grid structure. And they are having less inertia in comparison, very less inertia in comparison to the conventional power plants. So the power imbalance between the generation and the load will also create problems. So these are the major problems because of which we cannot directly integrate the DG units in the grid. Okay. So to overcome all these problems, the concept of microgrid was proposed in early 2000. Okay, so what are these microgrids? So this microgrid, it comprises of low voltage distributed systems with DG units, storage devices, loads, and interconnecting switches. It can be operated in and interconnecting switches. Okay. Now, the beautiful thing about, or the added feature of microgrids is that it can be operated in grid connected mode or in islanded mode. Okay, that is the main advantage of microgrids. So, like if there is some problem in this structure, it can be disconnected from here. I'm showing it in the islanded mode only, but like this is the external grid, so we can connect this. So then it will be a usual grid. Okay, it is incorporated into this. But if there is some problem either here or here, sorry. Yeah. So if there is some problem either here or in this section, then this can be disconnected and then it can be operated in the islanded mode. Okay. So now you see we have in this system, like we have this solar power, then this diesel generator, then this wind turbines also. So all these renewable generations are there, and we know that these renewable generations, so they are intermittent in nature and volatile also. So if it is operating in islanded mode, okay, then we need to worry about it, because if it is operating in the grid connected mode, what will happen, even if the slight power imbalance is there, that will be managed by this external grid. Okay, but if it is operating in the islanded mode, in that case it becomes very important to maintain, means it becomes a responsibility of the microgrid to maintain power balance. Okay, and that time this battery energy storage systems, they play a very important role. They help in power imbalance or maintaining the power balance. Okay, so these battery energy storage systems are very important part of microgrids, and they are responsible for reliable operation of microgrid also. And the loads also, variety of loads can be connected to the microgrid. Okay. Then the other important part is these controllers. Okay, these controllers, because see what is happening actually, if it is operating in the grid connected mode, the power deficit can be achieved by this external grid. It can supply the power to this microgrid. If you have extra power here, then you can trade that power with the external grid. Okay, so how to make all these decisions? These decisions are made by these controllers. Like if some fault is happened, then it need to isolate this microgrid. Then it will be the giving the command to operate in isolate mode. If it is operating in islanded mode, then like power balance is achieved with the help of these controllers. They will control the or help, or they will guide that when battery energy storage system has to come into the picture, or how much they have to balance. So everything is done by these controllers. Even if you are trading the power, how much power you can trade, that will be done by this controllers. So these are also very important part. Now, so we'll see in detail what are the major components of microgrid. So these are like loads, DRs, smart switches, protective devices, master controller, communication, control and automation systems. So let us first have a look on microgrid loads. Okay. So a microgrid loads basically can be categorized into fixed loads and flexible loads. Okay. So fixed loads, as the name indicates, it means that they need uninterruptible power supply. So we cannot alter these kind of loads, and whatever is the operating condition, they are not able to change their power consumption demand. Okay, so that must be satisfied in any case. So these kind of loads are given highest priority. So, and because they need to be supplied the power always, they are known as uncontrollable loads. We do not have any control, or critical loads, or non-responsive loads. Okay, because they are not able to adjust their power consumption according to the grid operating conditions, we say they are non-responsive loads. So what kind of loads fall in fixed loads? Like hospital loads, or nursing schools, or airports, or defense facilities. So they all fall under fixed loads. So we cannot control their power consumption. Okay. Then the other category of loads is flexible loads. So flexible loads, they are also known as controllable loads, or non-critical loads, or responsive loads, because these kind of loads, they are able to adjust their power consumption as per the situation in the grid. Okay, so this can be divided into further two types, like one is which could be deferred, so shiftable loads, and the other one is which could be curtailed, so curtailable or sheddable loads. Okay, so the loads which can be shifted or which can change their power consumption pattern, like if we consider electric vehicles or batteries, so they act as source and load as well. When they are charging, they are acting as the load. When they are discharging, they are acting as the source, isn't? So if like these EVs or PEVs or energy storage systems, they can be used to obtain the power balance, isn't? To obtain the required power balance in the microgrid. So if the source, like if the source generation or the generation is higher than the load, in that case you can use these battery or EVs or energy storage systems as loads. If the generation is less, then they can be used as the source. So they are actually shiftable loads. Okay. Then there are other kind of loads which are known as curtailable loads. So like if we see refrigeration, so it is not necessary to use it always, isn't it? So if there's a power problem or we need to obtain the power balance, we do not have sufficient generation, then these kind of loads can be curtailed. So these are the two categories of flexible loads. Now, microgrids DR, so distributed energy resources. Okay, so these distributed energy resources, they don't include only DGs, distributed generations, but also energy storage and responsive loads. Okay, because this energy storage and responsive loads, so they are also helping in maintaining the power balance in the microgrid. So they are also the part of distributed energy resources. Okay, now microgrid DGs. So microgrid DGs can be divided into two types, like dispatchable and non-dispatchable. So dispatchable, it means we are able to control the output of these kind of DGs. Okay, but the only thing is like they will be subject to certain technical constraints, like what is the capacity limit, what is the ramping limit, what is the minimum turn on or off time, like this. Okay, so but we are able to control their output within certain limits. The other kind is non-dispatchable. So non-dispatchable means we are not able to control their output because the input itself is not controllable. Isn't it? So in this category, renewable energy sources will come because we are not able to control their input. If the input is available, they will generate the power whether you need or you don't need. So we had to make certain arrangements to utilize them. Okay, so these kind of like renewable energy sources, they fall under non-dispatchable DGs. Okay? So we all know that they are volatile and intermittent in nature. So volatile, it means their output keeps on fluctuating, and intermittent means it is not always available. So because of this kind of nature of renewable DGs, it is very important to have energy storage system in the microgrid. Okay. Now these energy storage systems, basically actually they are the components which are providing flexibility and reliability to the microgrid. Okay, because of them only. So they are very important. Now for what purpose we can use energy storage system in microgrids? We can use them for energy arbitrage or frequency regulation or load leveling. So what is energy arbitrage? Energy arbitrage, it means that you are storing energy when the prices are low. Okay, and when the prices are high, you are selling that energy back to the market. So that is basically energy arbitrage. Now we'll see what is frequency regulation and load leveling in the next slide. Okay, so frequency regulation. So we know that the frequency always needs to be maintained within certain band. Okay, so if we see this example here, like frequency needs to be maintained within 59.95 to 60.05. Okay, so when this frequency is within this range, that time ESs, they are having this constant power. They're not charging and they are not discharging also. So they're not taking any power. But as soon as this frequency, it is going outside this band, so it is frequencies becoming higher. Frequency is becoming higher, it means that the generation is high and load is low. So if generation is high, so to maintain the generation and load, what you need to do, you need to increase the load. So we are charging these energy storage systems. So this charging, it helps in bringing down the frequency. So it comes back within this band. Okay. Now here the frequency is going down. So when the frequency will going down, the frequency will go down when the load becomes more and the generation is less. So to bring the frequency back to this band, what we'll do, we'll discharge this ESS, so the frequency again will come back within this band. So this is how this energy storage systems are used to maintain the frequency within this band. Okay. The next is like load leveling. So it is also similar to this one. Like we always want, though it is not possible to have the completely flat load profile, but we always want that there should not be like volatility, or it is very high or very low, or peaks and valleys in the load curve. We do not want this. So it should be maintained within certain band. So here, like if you see this, it needs to be maintained within 5 and 10 megawatt only. So here when the load is less, we want to bring this curve here. So we are charging this energy storage system. When it is here, so they are not taking any power, they're maintaining constant megawatt hour. Okay. And then once it is going up, again it is discharging. So this is how it works. This energy storage system, its charging and discharging needs to be controlled according to our requirements. So this is how energy storage systems can be used for load leveling. Okay. Then smart switches and protective devices. So these protective devices, basically, they are required in the system to identify the fault and prevent its propagation in the microgrid. Okay. And these devices and smart switches, they manage the connection between DERs and loads in the microgrid. So they disconnect and connect the line flows. And the switch at the PCC performs microgrid islanding by disconnecting the microgrid from the utility grid. Okay, so these are the smart switches and protective devices. Then a master controller is needed who will manage the operation of the microgrid. So it performs microgrid scheduling in grid connected and islanded modes, considering economic and security constraints. So microgrid scheduling, it means that it decides like how much amount of power will be generated by each generator, and when the battery energy storage systems or the responsive loads will come into the picture. Okay, so it will decide all these things. So some optimization problem needs to be formulated and needs to be solved by this master controller, and accordingly it will decide that how much should be the output of the generators and or the load responsive loads when they will come into the picture. So this needs to be decided by the master controller. Then it determines the microgrid interaction with the utility grid. So basically here the interaction means it exchanges the information with the utility grid about the generation, like forecasting. So whatever is the generation forecast available, it will exchange that information. Then about the schedule of this renewable sources and the energy storage systems, it will exchange that information, and the status of the breakers and other devices. So that needs to be exchanged with the utility grid, and it will also obtain the similar kind of information from the utility grid as well. Okay. So it is the master controller which will decide when to switch between the grid connected and the islanded modes. Okay, so it will be solely his decision. So it manages optimal operation of local resources, whether it is like energy storage systems or like responsive loads or generation. So optimal operation of all these local resources, right, is done by master controller. So then communications, control and automation systems, they are all required to implement these control actions and to ensure constant, effective and reliable interaction among microgrid components. So these are all the microgrid components. Now we'll see controls in microgrids. So let us first see what are the objectives of control system in microgrid. Okay, so like once this microgrid has started operating in islanding, or once the islanding happens in the microgrid, then the frequency of the microgrid will increase or decrease depending upon the power imbalance in the microgrid. Okay. And once the event which has made this isolation, okay, once that event disappears, then what will happen? This microgrid needs to be reconnected or resynchronized back to the utility grid. Okay, so we need to have like because see, when it needs to be resynchronized, it means you need to follow the frequency and voltage of the utility grid. isn't it? So you need to control all the DGs in proper coordinated way, okay? So that you are able to track the frequency and voltage of the utility grid. So that time all these DGs need to cooperate to adjust their power output and the voltage to track those of the utility grid. So we need a control for this kind of thing to synchronize the microgrid with the utility grid. Then to maintain power balance between the generation and the load, particularly in island mode of operation. Then to maintain stable voltage and frequency in the microgrid, to maintain quality of power injected into the utility grid, to harness maximum power from various renewable energy sources. So these are the actually objectives, and we may need several controllers to achieve these objectives. Okay, so this control strategy, it is implemented at two levels. One is at system level, which is like microgrid central controller. So it is almost similar to the one which we have seen as master controller. And the other is at component level. So like microsources will have a different controller, energy storage system will have a different controller, and load will have a different controller. So this is at component level. Okay. So we'll first see microgrid central controller. So this is at system level. So what are the tasks of microgrid central controller? So its tasks are to provide power set points for the DG units, as we have seen earlier, then economic scheduling, then to control peak load, to control non-critical loads during islanding, to minimize system losses, to detect islanding conditions based on the measurements at the PCC, to initiate resynchronization with the local controllers when the grid is restored, to monitor power flows through local generating units and the PCC, and to make islanding decision. So from all these control tasks, we can see that it is the responsibility of microgrid central controller to ensure reliable and secure operation and economical operation of microgrid. So all the tasks related to this has been associated with microgrid central controller. So it is his responsibility. Now, when we come to this component level control, so let us first see micro sources control methods. Okay, so basically, this control strategies, they are also depending upon the type of operation mode. Okay, like you can see here that in the grid connected mode, we are using PQ control method, whereas in the islanded mode, different controls are used. So let us first have a look on this grid connected mode. So when the microgrid is operating in grid connected mode, we use PQ control. So in this, what will happen? This reference value of P and Q will be determined by the utility grid. Okay. So accordingly, the microgrid has to generate this P and Q values. Okay. But when it is operating in the islanding mode, then we have two types of control. One is droop control and one is V by F control. So these both controls, they are similar to the primary and secondary control which we use in conventional power system. Okay, so droop control also, like it is for, we have two methodologies, PF droop control and QV droop control. So in PF droop control, we are controlling frequency by controlling the active power generation of the microgrid. Okay, and then in QV droop control, we are controlling voltage by controlling the reactive power generation. Okay, so this droop control, it is applicable when the small disturbances are taking place. Okay, this will be able to control only under the case of small disturbances. But if the disturbance is large, in that case, we need to shift to V by F control. Okay, so this V by F control, it uses PI controller and PIT controller to damp the oscillations in frequency and voltage. Okay, so this you need to remember, like droop control, it is used for small disturbances, and V by F control, it is used when there is large disturbance. Okay, so the control strategy implemented, the controller should be such that it automatically shifts from grid this PQ control to droop control when the islanding happens. Okay, so it should shift to droop control if the disturbance is small, and it should automatically shift to V by F control if the disturbance is large. Okay. Now, next is like energy storage system and load controller. So energy storage system, it should be controlled to absorb or release power quickly. Okay, in order to, because we are using it to maintain power balance, isn't? So they should be able to do their task quickly. Okay, so that we are able to reduce the influence of fluctuations in generation and load to the utility grid. The charging and discharging of the storage system, it is controlled according to the grid operating conditions. Okay, so this is what, like we have seen earlier, now that whether the frequency band is with frequencies within certain band, and or the load is within certain band. So these are the grid operating conditions which will decide whether the storage system needs to be charged or discharged. And also another important point is the state of charge of the hybrid storage system. It will also depend, like how much is already charged or how much we can charge that. So then the next is load controller. So it should be designed to shed the non-critical loads in case of power imbalance, particularly in the islanded mode of operation. Okay, so all this micro sources controller, energy storage system, and load controllers will be there. Now we use a hierarchical control structure in microgrid. So this hierarchical structure, it is basically divided into 3 layers. One is this primary level control, second is this secondary level control, and third is this tertiary level control. Okay, so these controls actually they differ on the like based on their speed of response and the time frame in which they operate, and also on the basis of communication infrastructure requirements. So the first level is primary level control. Okay, so it is also known as local control or the internal control, and it is actually it is the fastest control actually. So it operates on the time scale of the range of like 1 to 10 milliseconds. Okay, so this like because it is fastest, and further it uses only local measurements, okay, for its operation. So it uses only local measurements, so no communication infrastructure is required. And therefore what we have seen in the previous slide, like micro sources control, whatever group control and these, they fall under this group control. Specifically they fall under this primary level control because they are fastest in nature. Okay, and this power sharing control also, it falls under primary level control. Islanding detection also is actually because it needs to be detected very quickly as soon as the islanding happens, because your control strategy needs to be changed, so it needs to be detected very quickly. Okay, so that also falls under primary level control. Okay. Then on the top of this primary level control we have secondary level control. So it is also known as energy management system of microgrid. Okay, so this control actually it is slower in comparison to the primary level control, and it operates on the time scale of 1 to 10 seconds. Okay, so it actually it maintains the power quality by regulating the frequency of the grid, and it is also responsible for voltage, frequency restoration, and power flow synchronization control. Also, like here is power sharing control. So whatever load sharing ratio is managed by this or calculated by this primary level control, if there is any problem with this load sharing control, then this secondary level control can apply correction to that load sharing control also, load sharing ratio also. So it can apply that correction to this. Okay, so that is secondary level control. Then come to tertiary level control. So it is the highest level of control, and so it is responsible basically for microgrid supervision, generation forecasting, and economic dispatch and operation. So all these operations, they are related to they take certain time. So it operates on the time scale of order of few minutes. Okay, so this is like tertiary level control, and this tertiary level control is also responsible for any power exchanged with the main grid. So it will decide whether if the power needs to be exchanged with the main grid, then how much power needs to be exchanged. So this is done by tertiary level control. Then the architectures for secondary control. So I'm going to focus on the secondary control in this case. So different types of architectures have been reported in the literature, which is like decentralized control, centralized control, distributed control, and hierarchical control. Okay, so this is like decentralized control of microgrids. So we have this ng number of IIDG units, which are inverter interface DG units. Okay, so this inverter interface DG units are there, and each one is having this primary control. Each one will have this primary control with them. So when we talk about the decentralized control, so this secondary control, each IIDG unit will have its own secondary control. Okay, so that is the decentralized control. So you can see here, but the problem can you see here that these secondary control, it will be using only this information about this IIDG only, and based on that it will be producing some certain control action, but it is not having any idea about the system wide variables or any information about other IIDG units. So that is the drawback, because there is some coupling between these DG units. So some information should be shared, but it is not having any information. So it suffers from the lack of uniformity or consistency and coordination among IIDG units. Okay. Then next one, so the communication requirements are minimum here. The next one is centralized control of microgrids. So in centralized control of microgrids, what happens is data is all this measurement data and different data, they are gathered here in this, so they require communication infrastructure. So they will be collected at some centralized facilities, and based on this information, some control actions will be generated by this control. Okay, so the control action for all these IIDG units will be generated here and then will be shared with these units. Okay, so the problem here is that it needs this central computing and communication unit, but if any of this communication like this fails, then everything will be failed. This control will fail. So that is the problem with this centralized control of microgrids. Then distributed control of microgrids. So in distributed control of microgrids, what happens? We have like this decentralized control. So whatever were the drawbacks of decentralized control, we have overcome here, because we are using the transceivers sorry, which are exchanging information with this other IIDG units also. So they are receiving information from the other IIDG units also, and then based on that information, they are generating the control commands. Okay. And then comes is the hierarchical control of microgrids. So in hierarchical control of microgrids, we have two levels. Like we have this local decentralized control also. You see, each IIDG unit is having its own secondary control. Okay, and then it is also connected to this communication infrastructure. They are sharing this information, and this centralized secondary control is also used. Okay, so even if this one fails, then also this microgrid operation will be maintained. So this is like hierarchical control of microgrids. So now we'll go to stability in microgrids. So now we'll see the stability in microgrids. So all of you must be aware about the stability in power systems. So how does it differ in microgrids? So it becomes very important, though it is very important in power system also, but it becomes more important in microgrids because of the presence of different kind of components. So first is due to the presence of multi-energy source DGs, different types of DGs like solar, wind, everything can be present in the microgrid. Then interaction between different types of power electronic converters, because these are interfaced with the help of power electronic converters, then energy storage systems, then responsive loads. So many components which are able to change the power generation or the scenario in the microgrid. So because of that, stability issue becomes more important in microgrid. Then we have this AC microgrid stability. So as we have in existing power system, we have a small signal stability, transient stability, and voltage stability. Similarly, we will have these three kind of stabilities in microgrids also. So let us have a look like what are the reasons for instability in microgrid. So I'm focusing here only on AC microgrids only. So this small signal stability problem. So what do you mean by small signal stability? It is the ability of system, or the, you can say, when you are talking about the microgrid, it is the ability of the microgrid to maintain an acceptable equilibrium operating point in case of small disturbances, I think, which is like continuous change in load. Okay, so that is the small signal stability. Now, so small disturbances. Now, so why this small signal stability problem occurs? It may occur due to the presence of feedback controller. It may occur due to continuous load switching, which is taking place in the system, or insufficient damping in the system, or power limit of DGs. All these factors may give rise to a small signal instability in microgrid. Then transient stability, so it is the ability of the system to maintain an acceptable operating point or equilibrium point in case of large disturbances. What could be those large disturbances? It could be a fault which is leading to island formation. It may be a loss of DGs. It may be fault in AC microgrids or large load changes. So these kind of factors will give rise to transient instability problem in microgrid. Then voltage stability problem. So it is related, this voltage stability problem, it means like the system should be, voltage stability means the system should be able to maintain acceptable voltage profile for disturbances in the system. Okay, so how do we know this voltage stability? We use either PV curve or QV curve. So PV curve gives you the maximum amount of loadability, and QV gives you the amount of reactive power required at the load end to obtain the desired voltage. So the definitions are similar, and these reactive power limits or current limiters, induction motor load dynamics, or tap changers, or voltage regulators, these are the factors which can create voltage instability problem in microgrids. Then how can we improve this stability? So a small signal stability improvement can be achieved with the help of, like, if we are using supplementary control loops around each IIDG unit, or we are using power system stabilizers with each IIDG unit, or by coordinated control of micro sources or energy management system. This will help in achieving small signal stability improvement. Okay. Now, to obtain the transient stability improvement, so we know the main reason for transient stability problem is power imbalance, isn't it? So how can we achieve that power balance to maintain the transient stability? It is by controlling energy storage system, by load shedding, by control of power electronic converters, because they will control the output of DGs. Then adaptive protection devices, they will help in improving the transient stability. Then voltage stability improvement can be achieved with the help of voltage regulation with DGs, reactive power compensation with D-state count, which is a fact device which is to be used in distribution system, then advanced load controller or load shedding, and modified current limiters of micro sources. So now, stability analysis of islanded microgrids. So as I told you, that stability of microgrids is an important concern in the islanding mode of operation, not in grid connected mode, because then the stiff grid will take care of power balance. Okay. So, but if it is operating in the islanded mode, then IIDG units, they are responsible to maintain the frequency and voltage within their specified limits, and they should also share the load among them in a stable manner. Okay. Now, there are high chances that in the microgrid, when it is operating in islanded mode, under high disturbances or under large disturbances, the microgrid may become unstable. Okay, but it is desirable that if it is subjected to small disturbances, then it should be able to maintain the stability. So, therefore, this small signal stability, it is a fundamental requirement for the satisfactory and reliable operation of IIMGs. So we are considering here only small signal stability, because see, the microgrid is a small system. So if the large disturbance happens there, it is quite possible for them to become unstable. But even if the small system is there, because a small change, small disturbances can happen in the form of load change, that will happen. So at least under those circumstances, it should be able to maintain the stability. Therefore, we are focusing on small signal stability. Now, so how to perform a small signal stability analysis of microgrids? Okay, so the first step to analyze this small signal stability is to develop the state space model of the different components of microgrid. So we have to model like IIDG units, also networks and loads. All this modeling has to be done, and then from these models we can obtain the combined single model of microgrid. Okay. Now, when you obtain the state space model of different components, then you combine them to obtain the state space model of the microgrid, and then you need to linearize those equations. When you are performing this small signal stability analysis, we are considering small disturbances, so we use linearized equations there. So when you want to linearize the equation, then you need to obtain the steady state operating point around which you will linearize the equation. So how to obtain that steady state operating point? That can be obtained by using conventional power flow analysis or time step simulations, then solving nonlinear algebraic equations by iterative algorithms, solving systems differential equations, or modified power flow analysis. But we have used time step simulations. Okay. Now, once the steady state operating point has been obtained, then you linearize those equations for a small signal stability, and then eigenvalue based analysis we have used, which is the most common method to identify whether your system is a small signal stable or not. Okay. So this is the example microgrid which we have considered. So this microgrid is operating at 50 Hz frequency and 230 volt per phase RMS voltage. So we have used these 4 IIDG units. Okay, and these IIDG units, so each IIDG unit is comprising of this DG source, this voltage source inverter, and local control. Okay, so this DG source, it may be a photovoltaic or a fuel cell or a microturbine, etc. Okay, so we have considered this because we considered that microgrid is able to feed different kind of loads. So we have considered different types of loads. So we have considered here induction motor load, then constant power load here, then rectifier interface active load here, and then resistive load here. So these different types of loads are considered at these buses. Okay. So yeah, so 4 buses are there in the system, and if you connect this switch, it will be operating in the grid connected mode, but we have considered islanded mode of operation. Okay, and yeah, so now we'll see, before going to the next one, we'll see in detail this IIDG unit model, like what it consists of. Okay, so this IIDG unit model, so it is consisting of 2 sections. One is power processing section and the other is local control section. Okay, so this power processing section, it consists of this PWM inverter, then output LC filter, and the coupling inductor. And this local control section, it is comprising of this outer loop power sharing controller and inner loop voltage and current controller. Okay. So this PWM inverter. So why we are using this LC filter? We are using this LC filter because the output produced by this inverter will contain ripples, isn't it? So it will be pulsating AC output. So this LC filter is used to reduce or to attenuate any high frequency harmonics present in this output. So it smoothens this output. Okay, and this coupling inductor, it shapes the output impedance of this inverter and reduces any coupling between real and reactive power. And this power sharing controller, it is used to control the output power of the DGs, and this voltage and current controllers are used to control the voltage, output voltage and current of the DGs. Yeah. So now to obtain the state space model of microgrid, we divide the microgrid into 3 submodules. So one is generation submodule, other one is network submodule, and the third one is load submodule. Okay. So this IIDG unit model, one model is of 13th order. It will consider this outer loop power sharing controller, voltage controller, current controller, output LC filter, and coupling inductance. So everyone's order is written here, and then so one IIDG unit model is consisting of 13th order model, and we have 4 IIDG unit models. Then network submodule, so we have line model only, so which is taken as RL model, and it is of second order, so we have 3 lines. Okay. Then load submodule, so we have considered here active load submodule, which is of 10th order, passive load submodule, which is RL and CPL, so they are of second order, and dynamic load submodules, which is of 5th order. Okay. So once the state space models of these submodules are developed, then we obtain the state space model of IIMG by combining these submodules with the help of mapping matrices. Okay. So mapping matrices. So basically, what happens? Each node in microgrid, either it exports power or it imports power or current. So if the current which is going away from the node, it is taken as minus. If it is coming towards the node, it is taken as positive sign. Okay, so with the help of this kind of mapping matrices, we have mapped this generation to network, then network to load, and this is how we obtain the complete state space model of microgrid. Okay. Once, so this is showing you, so the order of the order is 77. 13, you can we can go back to the previous one. So 13 was for this, so you can calculate like 13 into 4, then 3 lines, 2 into 3, and then these kind of loads. So this gives the order of the microgrid is 77. So this is the state vector of the microgrid. And this state vector of the microgrid, it is comprising of the state vector of generation submodule, line submodule, passive load submodule, active load submodule, and dynamic or induction motor module. And this is the state vector of generation submodule, which comprises of the state vector of IIDG units, individual IIDG units. And this state vector of individual IIDG units, it is comprising of this factor. So basically, this first one is the angle between the common local and the common reference frame. Then this is the real and reactive power generation of IIDG unit. Then this is the voltage controller, like DQ axis state variable of the voltage and current controller. Then this is the inductor current, DQ axis component of inductor current, then DQ axis component of output voltage and output current of IIDG unit. Then this is the state vector of line. So we have like DQ axis component of lines 1, 2, and 3. Then this is the passive load, state vector of passive load. So passive load, so R load and CPL load. Then this is for active load. This is for induction motor. This is the disturbance. This is the input vector, control input vector. So this is disturbance vector also we have taken. This is the control vector of generation, and this is the control vector for active load. And this is the output. Okay. So this is the details about the complete state space modeling. It was not possible to discuss in detail, otherwise this will be totally mathematical. But we have published one paper which discusses only on the complete modeling of state space model of this microgrid. Okay. Now the case study. So we first want to analyze whether our system is small signal stable or not. So we have used eigenvalue and participation factor based analysis. And the dynamic performance has been analyzed with the help of time domain simulation. And here we have considered all the 4 IIDG units to be of unequal power ratings and with the induction motor load connected at bus 1. Okay, so there in the diagram I have shown inductive oblique induction motor load. So we have considered induction motor load here. Okay. So these are the test system parameters. So this is like IIDG1 unit was the lowest in rating, and then we are going to increase. So this IIDG4 is the highest in rating. Okay. So these droop gains also are accordingly. You can see this. They are also accordingly real and reactive power droop gains. And these are the inverter parameters, RIL parameters, these are the line parameters, and different load parameters are given here. Okay. So now, using based on the previous parameters, we have obtained the steady state initial operating conditions here. So you can see, because the ratings of DGs were increasing from 1 to 4, you can see from the active current like sharing. So it is increasing from 1 to 4. But reactive, you cannot say like this. Okay. So these are all the like IIDG voltage, DQ axis voltage, then DQ axis output current, then DQ axis inductor current. And this is the RIL parameters. Then these are the external parameters. So these are the bus voltages, DQ axis bus voltages, then frequency at each bus. Then this is like angle at each bus. steady state parameters for R and CPL loads, and so these are the steady state initial operating conditions. Okay. Now, so when we perform this model analysis, you can see, so we have used actually the eigenvalue and participation factor based method. So these eigenvalues are obtained by solving the characteristic equation of the state matrix of the microgrid. Okay, so you can see that these eigenvalues, so the 6 eigenvalues are coming to the right hand side. And this real part, basically, if you see this real part of this eigenvalue, they correspond to the stability coefficient and this damping of this modes. And this imaginary part, it corresponds to the frequency of oscillation of these modes. Okay, so these 6 eigenvalues are found to be unstable. Okay, because they are on the right hand side. And to identify that which state variables are influencing these modes, we have calculated participation factors. So participation factor, it is basically the association between the modes and the state variables. So larger the value of participation factor, higher is its influence on that mode. Okay, so it is important to know that. So if you notice these modes of interest, so these 5 modes, they are associated with the active load, which is RIL. So 5 modes are associated with the active load, and this one mode is associated with the induction motor. So you can see here that how this load dynamics plays a very important role in stability analysis. So now, and these are the states which have influenced these modes. Okay. So 6 are unstable modes, then 1 inter-area mode, which is also related to induction motor. And then we have low damping medium frequency modes also, which are all related to bus 1 or IIDG unit 1. Okay. So from here we obtain that this microgrid, whatever components we have taken, so it is unstable. Okay. And to verify this eigenvalue analysis results, we have performed time domain simulation. So simulations have been performed for 10 seconds, but we are showing it for better clarity. We are showing it only for 1 second here. So you can see, like this is bus 1 where we have connected induction motor. So the effect of induction motor, now there is a transient dip in frequency here. See? Though at all other buses it is not like that. So this induction motor is creating transient change in dip in frequency. Then if we see this active power output of these IIDG units, so you can see there are oscillations in this IIDG 1 and 3. So at 1 we have connected induction motor load, and at 3 we have connected RIL. Okay, and why this 4 where we have connected this resistive load? Why it is showing it like this? Because a very high power of about 25 kilowatt resistive load is connected there. So it is the reason behind this. And if you see this reactive power load, so again there are oscillations when at the bus where induction motor is connected, and this you see it is the negative response where IIDG2 is connected. So at bus 2 we have connected constant power load. So this constant power load, it offers negative incremental resistance. So it is proved here that this is giving this negative response because of that. Now if you see this current response, so current response, you will see that there are transient changes in the current response at bus 1 and at bus 3 where we have connected induction motor load and this RIL load. So it verifies all the results which we have obtained by performing eigenvalue analysis. Okay, so here we'll meet whatever are the observations. Let us summarize those observations here. So the small signal stability analysis revealed that 6 low frequency modes were there, 5 associated with RIL and 1 associated with induction motor. They lie in right hand plane. 1 inter-area mode associated with induction motor is present. Then 2 pairs of low damping medium frequency modes associated with IIDG unit 1 is present. Now the dynamic response of IIDG units showed that presence of induction motor, it causes significant transient dip in frequency, transient rise in active as well as reactive power response, remarkable transient changes in output current. So, and presence of RIL causes significant oscillations in active power response and output current response. And negative incremental resistance is offered by the CPL. So these are the summary of observations. So how can we mitigate this problem? To mitigate this problem, we need to develop a controller. So next we'll come to the controller design. Okay. If you have some doubts still here, you can ask.
Yes, participants, if you have any doubt up to this point, what the Trapti madam has explained till now, you can ask your doubt, you can clarify your doubt so that she can proceed. Or at the end of the session also, she'll give some 5 minutes, 10 minutes. So
Exactly.
if you have any doubt, then you can note it down meanwhile, and then you can raise your doubts. If nobody is having any query at this point of time, then she may continue.
Okay, so you can note it down. I'll start with this controller design also. Okay, and you can ask if you do not have right now, then you can ask at the end. Okay, so let us come to this controller design. So we have developed a hierarchical control for this microgrid. So here what we have done, as I told earlier in the hierarchical control, that we have a local secondary control with each IIDG unit, and then we have a upper level centralized control also. Okay, so here we have developed, like you see here, for each IIDG unit, we are using this decentralized controller. Okay, so this decentralized control is there for each IIDG unit, which is this is a local control, and this decentralized controller, so it is helped by this multi-input, multi-output centralized controller. And this centralized controller, it is receiving information. So we have placed, actually this controller is supported by PMU measurements also. So at each bus, to see that the system is controllable and fully observable, we have placed PMUs at each buses. Okay, so these PMUs, I assume that you people know about these phasor measurement units, which are able to provide the phasor measurements of voltage and current and other information like real and reactive power flows. Also, you can compute from those information. So they provide all this information. So we have placed these PMUs at all the 4 buses so that our system is completely controllable and observable. And these measurements are being transmitted to this PDC, phasor data concentrator, and then these information is being used by this robust optimal centralized controller. Okay, so then it is giving control command to each decentralized controller, and this decentralized controller is also giving command to this each IIDG unit, local control of each IIDG unit. Okay, so okay, the advantage of this controller is that if in case this centralized control fails, in that case also this decentralized control will be able to maintain the stable operation of the microgrid and the basic operation of the microgrid. Okay, so that will be still maintained. But this centralized controller, it will be improving the performance of this decentralized control. So basically the decentralized control was developed with the view to maintain or to ensure the stable operation of the microgrid. And then to enhance the performance of this local controllers, we are using this centralized controller. Okay. So this is the structure of the control. Now we will see the design procedure for this control. Okay, so the design procedure is like, first of all, we have already seen that the microgrid state space model needs to be developed. So that's already developed. Now in that microgrid state space model, we are incorporating this decentralized controller. Okay, so this decentralized controller is first incorporated in the microgrid, and then we obtain the small signal model. Okay, now because we are obtaining this input and output signals through PMU, so we want to reduce the cost associated with the installation of PMUs. So we are reducing, or we are selecting the effective input and output signals. Okay, so that is being done by using a method known as geometric measures approach. So that is used to select input and output signals. So we are not using all input and all output signals. So this number of input and output signals are reduced to reduce the cost. Okay, once this input and output signals are selected, then whatever model we have obtained, like you can see, we have considered only 4 IIDG units, and with 4 IIDG units and this kind of loads, we are achieving the order as 77 order of the microgrid. So if the order is higher, then the system structure will be complex, control will be complex, but we do not want the control to be complex. So what we have done, we have reduced the order of the model. Okay, so we have performed a model order, we have applied a model order reduction technique and then reduced the model order of this system. So from 77, I'll later tell you that what was the order of the system when we incorporate this decentralized controller there. And then we performed the model order reduction technique, and then selected input output signals were incorporated in that reduced order model. So once the reduced order model with selected input and output signals is obtained, then to have the impact of noise and disturbance, we have augmented this model with disturbances noise model. Okay, and then that augmented model is used to design the centralized controller. Okay, when you design the centralized controllers, it is very important to have tuned parameters for all the controllers. So we have also obtained the tuned parameters, and then these tuned parameters are given here. So this centralized controller is giving command to this power sharing controller of IIDG units and DC voltage and AC current controllers of RIL. So then they are giving command to these controllers. Okay, so these are the design procedure. Now we'll see in the step, like each step one by one we'll look. So first of all, so decentralized controller design. Okay, so this, if you are looking, this is the conventional power sharing controller, okay, which is producing this reference frequency and reference DXS output voltage of this IIDG unit. Okay, so this is the generator. Now this decentralized controller, what it is doing, it is modulating this reference. So based on this omega I, this is the output of this decentralized controller. So it is controlling this frequency, it is controlling this voltage. Okay, so these are the gains, Kp DECI, it is the real power gain and reactive power control gain of this decentralized controller. So this is output of the decentralized controller, and this is generated based on this alpha pi. If you are able to look here, this is the desired power sharing, and this desired power sharing is obtained from this. So these measurements are used. This decentralized controller is receiving this information through the centralized controller. So it is utilizing this total power generation, active power generation and total reactive power generation with the help of WAMS measurement. So this is the desired power sharing, and this is the actual power sharing which we are getting here. So based on the difference between the desired power sharing and the actual power sharing, this control command is generated. Similarly here, based on this actual power sharing, reactive power sharing, and desired and actual reactive power sharing, this control command is generated here. Now you can see the difference that here we do not have any integral, because the real power drop control is very accurate for this microgrids, but reactive power drop control is not that accurate. So to reduce the error, we have here incorporated an integral term. Okay, so so these are the droop gains, and these are the low pass filters. Okay, so now these are basically the main parameters for decentralized controller design, Kp DECI and Kq DECI, which needs to be tuned for optimal performance of the controller. So this tuning we'll see later. Okay, so this is how this decentralized controller, it is actually adding these auxiliary terms. Okay, these auxiliary terms are added to this conventional power sharing controller, and it modifies the reference frequency and DXS output of this controller. Okay, so now when we have incorporated this into the microgrid state space model, then you see the order changes to 81. Okay. And when we have performed, why this 12 is and 29 is coming? Because there are 29 input signals and 12 output signals. Okay. So this how we have identified with the help of geometric measures approach, we have identified that 29 input signals are there and 12 output signals are there. So this slide shows actually that selection, how we have selected input and output signals. So this geometric measures approach we have used, which utilizes normalized and orthogonal eigenvectors ui and wi corresponding to the ith eigenvalue. Okay. And then geometric measures of observability associated with the ith mode is defined like this, and geometric measures of controllability associated with the ith mode is defined like this. So we have calculated these values, and then a higher value of the observability and controllability measures that represents the most observable and controllable input in damping the mode of interest respectively. So we have calculated these values for all the corresponding to all the eigenvalues, and from there we have selected the highest high value of the those inputs which are having high observability and those outputs which are having high controllability. So considering the worst case of disturbance at all buses, the most observable signals are found to be 29 and most controllable signals are 12. So this whole analysis has been done in depth, and then we reached the conclusion that we should consider inputs as 29 and outputs as 12. Okay. Then model order reduction. So we have applied Schur balanced model reduction procedure to the linearized model, and then selected input output signals have been incorporated in the reduced order model. So this is basically the error bound, which is basically the infinity norm of the difference between the full order model and the reduced order model. So you can see from this figure that when we plot this error bound with respect to the order of the linear model, you can see that from 40 to up to 81, like this error bound is almost 0 or very small. But as we go on to reduce the order below 40, then this error bound is increasing substantially. So from here we can conclude that we can reduce the model order up to 40. Means it only 40 state variables will be considered. Okay, and then this shows you this to confirm this thing. We have also plotted singular value plot with respect to this. So if you see, this is the 81 and 40th order, so they are almost inseparable, isn't it? But as we go below 40th order, then this is increasing, it is deteriorating, isn't it? So from here also we confirm that we can reduce the model order up to 40th value. So this is the reduced order model of the microgrid. So we have reduced to 40. So the model order now is 40 and the inputs are 29 and the outputs are 12. Okay. Now, so after model order reduction, let us come to this centralized controller design. So here we have used modal form of reduced order model of the microgrid with selected input or output signals, because we found that for this kind of specifically when the dynamic loads are present, this form is able to perform. Though this conventional LQG is already known that it is robust, but it was not able to perform the way we wanted the controller to perform. Okay, so we have modified it in the model form. So this reduced order model augmented with noise and disturbance model is transformed to the model canonical form using the real Schur decomposition. And this the transformation matrix that relates the original state variables and the decoupled model variables is then obtained. And then model augmented model is used to design the centralized controller based on extended LQG. So this is the model based extended LQG, which is connecting this Kalman state estimator and this optimal output feedback control gain with linear quadratic regulator with prescribed degree of stability. So this central control problem, so it is divided into two subproblems. One is the optimal estimator of the state, which is performed by Kalman estimator, and then optimal output feedback control problems. So this optimal state estimation, it is based on Kalman estimator theory, and the optimal output feedback control, it is based on linear quadratic regulator with prescribed degree of stability theory. So in this particular LQR PGS, it has an advantage that it it basically prescribes a certain degree of a certain distance, minimum distance, which needs to be maintained from the imaginary axis. So it always ensures that your system will be stable and it is keeping a certain margin from the imaginary axis. So that was the reason to use this LQR PDS. Okay. And then the gain metrics of both the optimal output feedback control and the optimal state estimator that is dependent on the diagonal weighting matrices. Okay, so we need to tune all these parameters. Okay, now this centralized controller, you see, so it is giving the control commands to this modified power sharing controller and to this RIL controller, voltage and current controllers of the active load. Okay, so this is basically the voltage correction factor, which is modulating the voltage of this or output of this modified power sharing controller. It is modifying this. So this modified reference is produced for this voltage controller. Because this is modified, so it will modify in turn this. And because it is modified, it will modify in turn this. This is how they are all correlated. Okay. And then here is a control signal from the centralized controller to this DC voltage controller and to this AC current controller. So these references are also modified. Okay. Now, so once this has been done, now we need to tune the hierarchical controller parameters. Okay. So see, usually these parameters, we cannot tune them by trial and error, see? But we can tune them by formulating certain optimization problem. Okay, so we wanted our controller to give a good transient response, and it should be robust enough to sustain small signal disturbances also. Okay, so these were our objectives. So we found that these objectives can be achieved by minimizing these two functions. So this is, we have formulated a bi-objective optimization problem. So this is basically the second norm of the optimal output control gain matrix. Okay, and this is the condition number of the eigenvector matrix of the IIMG, inverter interface microgrid. Okay, so this is the condition number of the eigenvector matrix of the microgrid, and this is the second norm of the optimal output control gain matrix. Okay, so these are basically the optimal parameters will obtain as x1, x2, x3, x4, which comprises of this decentralized active power gain and decentralized this reactive power gain, and the diagonal values of this is for Kalman estimators parameters, and this is for optimal output control gain matrix parameters. So this this bi-objective optimization problem has been formulated, but we notice that these two objective functions, they are conflicting in nature. So to solve that, we adopted non-dominated non-dominated sorting genetic algorithm. Okay, this has been used because it will provide the Pareto optimal solutions, and then from this set of this Pareto optimal solution, we can find out the most effective solution. So these are the NSGA2 parameters which we have used here, and a potentially 28 number of Pareto optimal solutions have been obtained. So post Pareto analysis is performed to obtain the most effective Pareto optimal solution. Okay. So how did we obtain that? So we basically clustered this 28 number of solutions. We have clustered into two groups. Okay. And then this cluster 1 contained this 19 solutions and cluster 2 contained this 9 solutions. And this 19, so whichever is the cluster centroid or the solution closest to the cluster centroid, that is considered as the representative solution. Okay, now so we have first identified actually knee cluster out of these two, because anyone, this also could be better, but we identified the knee cluster, and the knee cluster is the one in which if you change, if you make a small change in one of the solution, then it should lead to a large change in the other solution. So we identified that the knee cluster is the cluster 1, so its representative solution is selected as the optimal or the most effective Pareto optimal solution. Okay, so that is taken. So now this shows you the tuned parameters of the hierarchical controller. Okay, so these are the decentralized controller parameters, and these are the centralized controller parameters. Okay, so you can notice that here this optimal output state feedback control, this QKMG. These are having much larger values in comparison to this RKMG. Okay. So now we'll see the performance assessment of the controller. Okay, so we have again performance assessment has been done by eigenvalue and participation factor, and we have not done participation factors yet, actually eigenvalues. And then we have performed time domain simulation also to assess the to validate the performance of the controller. So this part A, it is the eigenvalue analysis for the open loop microgrid. So you can see that it is here, these 7 modes which we have seen earlier were lying on the right hand side, and here this is based on state based hierarchical controller. As I was showing that it was not performing as we were wanting. So this is the state based hierarchical controller, and this is the model based hierarchical controller which we have proposed. So you can notice that because the certain I told you we have used LQR PGS, which maintains a certain minimum distance from the imaginary axis. Okay, so that distance we have specified as 100. So you can see that it is able to maintain, in both the cases, it is able to maintain that distance from the imaginary axis. So both the controllers are able to maintain the stable operation. Okay, so we can look into this detail that this are all lying in the right hand side. With this also it has moved to the left hand side. With this also it has moved to the left hand side. But see the difference in the values. Okay, if you see the frequency here is much higher, but here the frequency is low. But if you compare the damping in this case is much higher, which is more important. Okay, so this one was able to perform, the model based hierarchical controller was able to perform better in comparison to this one, but both were able to maintain the minimum distance. Okay. Now the time domain simulation results. So this is linear model. So whatever linear model we have used for this small signal stability analysis, we have performed time domain simulation on that model. And to confirm, so this is for open loop. So you can see this frequency also, it is increasing continuously. And this burst voltages are also there increasing continuously, which shows that the system was unstable. But if you see this deviation in frequency for the state-based and this model-based controller, you can see that both are able to stabilize the system so quickly. Okay, but the thing is, this with the state-based, this amplitude is high and it is taking comparatively longer time in comparison to model-based controller. Okay, so here also you can see that this are all stabilized, means both the controllers are able to stabilize the deviations in voltages. Okay, now to see in more details, this shows you these parameters. Okay, this table shows with the help of these parameters, you can see the settling time. So you can compare here. The settling time is of the proposed controller is very less in comparison to the state-based controller. However, its peak overshoot of the proposed controller is larger than this one. Okay, no, sorry, the peak overshoot is larger in few cases here. Is larger here in the proposed one. So, but the other two things, settling time and peak amplitudes, were less when we used model-based controller. So this has validated our results previously. Now, to further validate what we have done, we have performed time domain simulation results on non-linear model also, and then we have divided the simulation time into 3 periods basically. You can say this is a steady state period. So till 0 to 1, it was operating under steady state mode. No change was done. And then we have applied a step load disturbance of 2 kilowatt at all the buses, considering the worst case. So we have applied 2 kilowatt step load disturbance at all the buses. And then, so at t is equal to 1 second, this disturbance is applied. And from 1 to 2 seconds, the controller was not activated. Okay? It is the open loop period only. But at t is equal to 2 seconds, the controller is activated, and at t is equal to 3 seconds, controller deactivates, and this is also removed. This load disturbance is also removed. This has been done to visualize clearly the effect of the controller's design. Okay, so this you can see here. It shows you the frequency. So this frequency, once it settles, then this is the open loop period. So here the variations in frequency you can see, and as soon as the t is equal to 2 seconds, the controller comes, it settles here. See? So then the time domain simulation. So here actually we are showing, you notice it is 1.2 to 1.8 seconds, and this is 2.2 to 2.8. So this is like open loop and this is closed loop. So this is showing you active power response. So here it is varying, but here it is stabilized. Again, this is current response. So here it is varying and here it is stabilized. Then time domain simulation results for this voltage at all the buses, or at all the 4 buses. So you can see this is 1.2 to 1.9 seconds. So it is coming like this. It is oscillations are there, but here these oscillations are dead. Okay. And to see it in more, we are showing you in next slide from 1.85 seconds to 1.9 seconds. These variations are clearly visible, and this is like oscillatory. So the variations you should notice are very small. Then this shows you for the current 3-phase currents of output currents of the DGs, all the 4 DGs. So this, during the open loop period, there are oscillations, and then they are stabilized during this closed loop period. Then this shows you the active power of the active load. So again, these were the oscillations, but here it is completely remove these oscillations. Then DC voltage of the voltage controller, and then this is the speed of induction motor. So earlier it was varying like this, and now it has stabilized. Then torque of the induction motor, so again it is stabilized. You see the variation. Don't go to this directly these shapes only, but the variations also you should notice. So here we can conclude. So the proposed this hierarchical controller, it provides supplementary control signals to the modified power sharing controller of each IIDG unit, as well as the DC voltage and AC current controllers of the RIL. Then supplementary control signals were able to stabilize the unstable modes caused by dynamics of CPL and RIL. Further, these signals also improve the damping ratios of the low damping modes caused by the dynamics of the first IIDG unit, corresponding to the connection of dynamic induction motor load. The proposed hierarchical controller was able to settle the deviation in the frequency and the voltage at the 4 buses within 30 to 45 milliseconds. So further, it provides faster response than the hierarchical controller based on state-based extended LQG approach. Okay, so actually you can say that whenever you analyze the stability, the load dynamics, it plays a very important role. So you should always try to consider the load dynamics. Don't consider the static load. It will not be that important, but the load dynamics is very important. And we have also designed, like earlier, when we have not considered this induction motor load, we have also done with only CPL and RIL also. So that time we have designed like decentralized, centralized controller, and they were able to stabilize the system. But when we added this dynamic induction motor load, that time those controllers were not able to perform that. Okay, so as you add complicated loads in the system, that time your control design also needs to be checked properly. Okay, so I would like to end here, and I'm open to any questions.
Thank you very much, Trapti madam. You have explained the controller, centralized controller, and the different types of the controller in a very extensive and in-depth way. Modeling as well as analysis that has been carried out by you over the period of time, and that is sometimes it is very difficult for the participants to follow and understand each and everything, which might take a couple of years to reach to that point. So that is very true, madam. If you have any question, participants, please you may ask. She will be probably sparing 5 minutes, 10 minutes on those question answer session. If somebody, meanwhile, if somebody is gathering their question, madam, I would like to ask a very simple question. Actually, I'm not the person from the power system, so my question may not be so valid at this point of time. As you said in the end of the presentation, that the dynamic kind of the load means, is it the motor load is not being changed during the simulation, isn't it?
No, it is actually, see, induction motor itself, when it is not a static load, isn't it? It's
Yes,
changing. Its speed is changing, torque is changing, everything
yes,
is
yes,
changing, isn't it? So that induction motor itself, it's having certain dynamics which you need
yes.
to consider. Okay,
Okay,
so you
okay,
should always look to have what kind of possible loads this microgrids can feed,
okay.
isn't. So all those kind of loads you should try to incorporate. Like basically, how can we think about this kind of things? We can consider the college campus itself as a microgrid, and
Yes,
then you try to understand that what different kind of loads will be there.
yes, yes.
Based on that, you can model, and you should try to include all those models.
Okay, okay. So you mean to say that it matters a lot, the type of the load, the
Exactly,
uh, on the
exactly.
controller design.
Yeah, yeah,
So it may be possible that the one controller which is designed for certain kind of the load may not work so satisfactorily with the other kinds of the loads.
exactly, exactly.
Okay, yes, that's what I have a confusion.
Hmm.
uh, One more thing that I'd like to ask is, in which the as far as the computations are concerned that you have shown in your presentation, it is
Mhm.
so number crunching computation, I guess.
Mhm.
So is it done in MATLAB or some other kind of?
No, all this work has been done in MATLAB.
Okay, okay. And it is in the real time kind of situation, or that
No,
you pre-decided, you pre-feed the data and then you run for that, and how long it takes
no,
to
no.
come?
Actually, see, yeah, it takes a longer time because this part we have not done in real time simulation environment. Okay, so by that time we didn't have that facility when this work was done. So it was done in MATLAB Simulink only. Through that only we obtained the steady state initial operating conditions, and then the controller was designed. Some coding was also required to be done.
Yes, sure.
As you can see, that controller design itself was very complicated because of the structure of this microgrid which we have taken, isn't? And then uh, the tuning of the parameters. So
Yes,
there are actually at different levels we have to make different decisions, and for each decision we should have something which we can convince that why we have taken that particular decision, isn't? So we cannot randomly adopt the this values also. This
yes, it is not a
yeah,
trial and hit kind of thing.
yeah. So we
Yes,
need to formulate like what we want to obtain, then different kind of objective functions we have explored that which will be able to work. So once you tune, then also like as I told you that though we have used NSTA2, but then so many optimal solution, Pareto optimal solutions are there.
yes,
Out of that, which you will select. So we have to go into the depth, like why only two clusters? Isn't anybody can ask why only
yes,
two
yes,
clusters? Then how you are identifying? So different, which we have. I have skipped actually. It is very complicated. So few things I have skipped.
yes, yes. Deliberately, you have to do that.
Yeah. So some Silhouette coefficients we have calculated, which tells that only two number of clusters should be there. Then
Yes,
out of that, only from which cluster you will select the solution. So different methodologies we have explored in the literature, and based on that, we went by this thing.
yes, yes. Definitely, definitely. uh, Participants, if you have any question, I guess what I have asked, that some of you might have the same question bubbling in your mind. So if any other question that you would like to ask, madam, if possible, can you share that the literature which is published by you on this particular topic, if it is possible, or if it is from open source, and if you can
No,
share
it
the
is
link with
not
the
actually.
participants?
No. This particular paper was published in IEEE Transactions on Industrial Informatics.
Okay, okay.
So you can search by like hierarchical controller design, a,
Even the title and that.
a two-level hierarchical controller.
Okay,
Search by that name. If you type, I think that will come.
okay. Participants, if you do not have any question, then
Hello,
we
ma'am.
may.
Yeah.
Ma'am, there is one question in chat box. How to differentiate between current deviation due to load change and fault-driven change in current?
That is a different question. Actually, see, here, if the current change, see, I think that is actually problem in microgrid, isn't it? Because we need, that is one of the issues in microgrid, because when we are using these power electronic devices, those conventional protective devices are not working because they themselves are not able to distinguish between the fault current and the load current, isn't it? So this is difficult to answer because this is itself a research question where people are trying to identify, they are trying to develop different kind of protection devices. Okay, so this protection of microgrid itself is a research problem.
Yes, it is a completely different thinking that it requires in terms of the small clusters of the microgrid.
What is the next question is like, what is permissible value of undershoot
or overshoot of the bus voltage and the load changes?
Load changes is not under our control, isn't load change we cannot control. It is on the customer end. He doesn't want to, whatever is his requirement, he will change immediately. So that is not under our control. But bus voltage, so basically I think the percentage overshoot, not in terms of like percentage overshoot or undershoot, I will tell you, but I think the values on the this limits, voltage limit you can consider, isn't? I do not remember exactly the what is the, because I'll not tell you the wrong data, but I do not remember exactly the percentage undershoot and overshoot.
Okay, I think now there is no question from the participants. So, madam, again, thank you very much for sparing your time and being a resource person for this particular FDP. Definitely, it will be helpful to the participants as the topic is very informative and it gives a very in-depth understanding of the control. So, again, on behalf of entire team of the FDP, Sarvajanik College of Engineering Technology, I'd like to thank you. Thank you very much, madam.
Thank you. May I leave now?
Yeah, ma'am, you may leave. Thank you very much. Participants, the next session will commence at 2:30 and that will be conducted by Dr. Premalata Jaina, IIT Roorkee, on Introduction to the Smart Grid Technology. You are requested to be on time and please join the session at 2:30 sharp. Thank you.
Stop करो.